Today I'm going to talk about the Beady Rings model. It's one of the exercises of our course, and I will discuss the model itself, what's the idea, and I'll start implementing it following the template I provided. Remember that the implementation I suggest here is not mandatory. You can erase all the code and start again and do your own implementation. The idea is that I provided some code. You just need to create the helper functions to make it easier for you to implement it. But feel free to change it. So let's see what's the Beady Rings, what's that model that we saw in class. Let's find out it here. If we go to our week 2, we can go to our discrete simulation class. I'm going to open, there's one slide that's important where we show how the model works. So here's our model, and what matters here is that we are trying to simulate a certain urban pattern that by assigning to a grid a duplet that is composed of closed space or private space and open space or public space. We are going to use both names, closed and open, or private and public, and they're connected by an entrance. We have a grid. Let's start with a very simple grid, 4 by 4. And the first time step, we add this doublet at any point that we can have the public and the private space. And for the second step on, we are going to have some requirements. The idea is that we have two requirements. The new doublet can be inserted in any position following these requirements. The first requirement is that the new public space has to have an edge, a full face-wise adjacency with a previous public space. So you can see that in the step 1 we had, with step 0 if you want to call it, we had this doublet here. In the step 1, this new doublet shares an edge in terms of public space. So that's the first requirement. The second requirement is that the private space has to follow at least, like, there are two cases that are legal for the private space. Or the private space shares an edge, like here, or it's isolated, like in this step 2. You can see that the public space shares an edge here, but the private space is isolated from previous private spaces. What that means, in other words, is that we cannot have a case where the new private space only shares a vertex with the other private space, with the previous private space. So this case is illegal. You need to share an edge. If you only share like a vertex, it's illegal, and you cannot do that update. So let's try to code that. Let's go to our template. Let's see here. Let's see, in this first part of the video, I'm going to understand how our implementation works. So first of all, let's draw a grid. I think this is going to be really helpful. I'm going to draw I'll use 4 by 4 just to keep the same example and for simplicity. So let's say 1, 2, 3, 1, 2. Yeah, this is not the best grid, but it's going to be good enough. Yeah, all right. So this is our grid. Let's say we have two coordinates. Let's call them, we can call y and j, x and y, and I is going to be this. It's going to define which column we are in, and j is going to define which row we are in. So for example, if I say 3, 1, that'll be 0, 1, 2, 3, 0, 1. So it's this here is 3, 1. Okay. Um, so that's the basic representation. However, we are not going to store the grid as a to-do list in Python. We are going to store positions using sets and lists. The idea is that to represent this full grid, I could have a set containing all positions. For example, 0, 0, 0, 1, and so on. In this case, until 0, 1, 2, 3, until 3, 3. Okay, so I can store this inside a set. And the advantage of the set is that we can do operations like union, intersection, subtraction, and we can check containment, and these operations are very efficient. Okay. So let's go to our implementation and let's see how we are initializing the variables. Just adjusting the layout here. Okay, I think that's all right. So let's go to our interactive part first. We are using the interactive setting here. We are using the reset with this Boolean toggle, and we have a timer. So let's see what happens when we reset the system. When we reset the system, we initialize a bunch of variables. And in this case, we opted to do the first update. I mean, we could implement in a way that the first update is done after the initialization in another part of the code, but we're going to initialize the variables and do the first update. So when we initialize it, we also generate the first position and we update our variables. So these are the steps we have here. We have empty set equals this, private set equals set. So basically empty set has all the positions for the grid. So we can see that size, actually it's coming from, if we see size, it's coming from this slider, so we can move back to 4. This slider doesn't allow 4, so I'm going to change the limits, 4, and now we can have 4. Nice. So now we have 16 positions stored in a set. We have a private set and a private list. This is optional. I'm just trying to show how you can store either in a set or in a list. In our case, we are going to use both, but you can use only once. We also have a public list that stores the positions of the doublets that are the public spaces that we assigned to the grid. So the private list and private set, they store the same thing. They store like the positions of the closed space or private spaces, and the public list stores the positions of the public spaces or open spaces. And we have an interesting variable that's called public frontier, that it stores the current frontier of our public spaces, the available frontier, in the sense that I'll show an example. Let's see public frontier here. Let's imagine that my grid, I'll do a 4x4. This frontier will make our life really easy to select, to sample the next candidates. So let's create a 4x4 grid here. Much better now. Okay, so I'll use, I'm going to use a very simple notation. I'm going to say that when these are, let's say the public space, I'm just drawing the boundary, and the private space I'm actually filling. So this is our first. Let's see which one looks more like a private. Okay, so this is going to be our private space. So it looks like we have walls here, and this is going to be our public space, like in a street. So let's say the second one, we assign it here. You see that it's much easier if I assign the next doublet starting with the public space. And let's say that the private space is here. in this case, let's see what's our frontier. Our frontier is composed of, right now, should be uh, the neighbors of the public cells that I have that are unoccupied. So this will be part of our frontier. This will be part of our frontier. And when I say neighbors, I'm just thinking the basic top, bottom, left, and right. So this will be a frontier. This will be a frontier. And the reason this is a frontier is because, as I mentioned, now we have the system in this state. We can sample our next uh, candidate for public and private space using this frontier. So we can say, well, maybe my next portion of the street, my next public space can be this one, or maybe it can be this one, or this one, or this one. So I don't need to sample from the whole grid. I can sample only from these 4 positions, and then I can say maybe it's here. Maybe this is my, I just need to change to yellow. Okay, so it's going to be the same, but that's fine. So maybe my new street is here, and now as I select this to be my new public space, I have the options of having the private space in the 4 neighbors if they are not occupied. So in this case, I cannot assign it here, I cannot assign it here, but I have the options of private spaces here. And if I assign it here, you see that I break one constraint because it's going to share a vertex with this one, but I can assign it here. So this is going to be my new private space that shares an edge with a previous one. Okay, so try to take a look and understand these variables. In the next video, I'll start implementing the first functions.